In this video, we're going to talk about Green's theorem. So there's actually two forms of Green's theorem, and one is the circulation form, the other is the flux form, and we'll talk about both. So first, let's consider a region R in the xy plane that's going to be enclosed by a curve. We'll call it C. So we have this curve C, okay, and this is a simple enclosed counterclockwise oriented curve. So C is simple, closed, and oriented, as you can see, counterclockwise, and then it's enclosing the region R. Now R is a simple and connected and simply connected region, basically meaning there's no other parts of R anywhere around here and there's no holes in R. Now also we want to consider a vector field F, so some random vector field here, okay, and we are interested in taking the line integral of the vector field. So our vector field is going to be defined as F, which is going to be defined as little f of xy, comma, little g of xy. Okay, now little f and g have continuous first partial derivatives in this region R. Right, so we are interested, like I mentioned, in the line integral over our closed curve C of f of our vector field, so f dot dr. Okay, and then just note where dr is the vector dx dy. Okay, so basically what Green's theorem does is it takes this line integral and it relates it, or the line integral of this vector field, and it relates it to the double integral of the region R. Okay, so we have this integral here, so basically this is it. This is the theorem. The line integral of f dot dr, this is going to be the same as our line integral on our closed curve C of little f dx plus little g dy, and then Green's theorem says that this is the same as the double integral over our region R of, now this is the interesting part, the partial derivative of g with respect to x minus the partial derivative of f, little f, with respect to y. And this is dA. Okay, so this is actually going to make it easier to evaluate line integrals in some situations. It's a really useful theorem. Now this part here, this integrand, this is what we call the curl, or two-dimensional curl. So to say 2D curl. Okay, and this is of our vector field F. Right, now if this curl is 0, then we say that F is irrotational, or it doesn't have any rotation. So note, if the curl is 0, then F is irrotational. No rotation. Irrotational. And then also, this implies that F is conservative as long as R is simply connected, a simply connected region. Conservative. Okay? So if you want to figure out if your vector field is conservative, as long as R is simply connected, you just evaluate the curl and see if it's 0 or not. Alright, so let's go ahead and look at an example of using this theorem. So for example, we're going to consider the vector field F, which is equal to 2y comma negative 4x, and our region R is going to be defined as the region bounded by y equals sine of x and y equals 0. And this is going to be for x between 0 and pi. Okay, and what we want to do is we want to evaluate the line integral of our vector field over our curve C, our closed curve C. So we want to evaluate f dot dr, the integral of this. line integral. Now, by Green's theorem, we get to use the partial derivatives here. So we need to identify little f, which is 2y, and little g, which is negative 4x. And so we want the partial derivative of f by the theorem with respect to y. So this is just going to be 2. And then we want the partial derivative of g with, again, through the theorem, with respect to x. And it's just going to be equal to negative 4. So then our line integral, which we're trying to evaluate, f dot dr, by Green's theorem, is the same as the double integral over r. And the theorem, just recall, it was the partial derivative of g with respect to x minus the partial derivative of f with respect to y. Okay, dA. And so if we simplify the integrand, it's just negative 6. And so let's define the limits of integration for our region R. So we know this is negative 6. Now, if you go back, y depends on x, so we're going to evaluate this integral with respect to y first. So y goes from 0 to sine of x. So we're going to evaluate dy. And then we'll consider x, and x goes from 0 to pi. Okay? And so this is a nice integral. We just get, so again, this is from 0 to pi for x. We get negative 6y evaluated from y is 0 to sine x. And this gives us negative 6 sine x. And then when we evaluate at 0, it's just going to turn into 0, so that term is gone. And now we integrate the outside integral. So let me move up here. Okay, so we have negative 6 times cosine, negative cosine, because the integral of sine here is going to give us negative cosine x. And this is going to be defined for x from 0 to pi. Okay, let's go ahead and simplify this real quick. This turns into positive 6 cosine x of pi minus positive 6 of cosine of 0. Okay, cosine of pi is negative 1 minus 6 times cosine of 0 is 1. This gives us negative 12. Okay, so this is the value of our line integral of our vector field, and we evaluated it using Green's theorem. So this is a very nice theorem to use. This actually, this process of evaluating this integral was not, this double integral was not bad. Now, if we didn't use Green's theorem, then I'll talk about that a little bit, and you'll see why this was the nicer way to go. So imagine that we didn't have Green's theorem and we wanted to evaluate the same integral, the same line integral. So let me just remind you, well, actually, let's just draw it. So we have our region R, which is going to be bounded by y equals 0. Let's use a couple colors here. So y equals 0. Okay. So it's going to be bounded by y equals 0. And then also, it's going to be bounded by sine of x, y equals sine of x. Okay, well, we know that sine of x is 0 at 0. At pi over 2, we get 1, and at pi, we get 0. Okay, so there's our sine of x. So we don't actually need this part out here. Our region R is in here. Okay, and this is going to be oriented, the curve formed by this is going to be oriented counterclockwise. Okay, and so now if we wanted to evaluate this without Green's theorem, what we would actually need to do is we would have to consider this top curve bounding our region and the lower curve. So we would actually have to say our line integral over our curve C of f dot dr would be equal to the sum. If we call this, let's use another color real quick. If we call this bottom boundary C1, we would have to say the integral line integral over C1 of f dotted with d, let's call it R1, okay, because that's going to depend on the curve parameterized to define this lower boundary. And then we're going to add the integral over this top curve, we'll call this C2, and that would be f dot, we'll call it dr2. Okay. And so we would have to parameterize this lower boundary and this upper boundary, this curve down here and this top curve up here. And so what you would have to end up looking at is, okay, let's go ahead and come up with R1 and R2 real quick. We want to evaluate this whole integral. We already know the answer. It's going to be negative 12. It would just take a lot longer to get there. So this bottom curve, it's nice. It's not going to be bad at all. It's just going to end, this integral is going to end up being 0. But if we parameterize this here, we would have that R1, so C1, this bottom red line here, we would get that R of R1, and this is going to be based on the parameter t, would be the vector defined curve t, so t is ranging from 0 to pi, okay, and 0. It's t comma 0. Okay, so we would have to take the derivative of this, plug it in here, and then use our vector field. Let's just remind you what it was real quick. F was defined as 2y negative 4x. So this, we would take 0 to be y, t to be negative 4. We would place that in f, dot it with the derivative of this. Okay, so that one's not bad. Now, when we consider this top boundary, this top curve, the parameterization for this one, we'll call it R2 of t. Well, this one, let's start with the y component. It's going to be sine of our parameter t. Now the x component, it's going to range from t all the way to pi, pi being the largest, so it would be value, so pi minus t for the x component. So then you would have to take the derivative of this, place it into our integrand, and dot it with, so notice our x component is pi minus t, so you plug that in here. The y component is sine t, you plug this in here, and you would dot that with the derivative, and that would actually end up requiring integration by parts. And eventually, once you do all this, you would still end up with negative 12. Okay, so Green's theorem has very nice applications and makes evaluating certain integrals much, much easier. All right, so that was actually the circulation form. So this form of Green's theorem, let me just remind you what it was real quick. So the integral, line integral over our closed curve C of f dot dr. I'll skip the intermediate step, but basically this became the double integral over our region R, and this was the difference of the partial derivatives, the first one being the partial derivative of g with respect to x minus the partial derivative of f with respect to y. Okay, this is called the circulation form. Circulation form of Green's theorem. Okay. Now we're also going to consider the flux form, but before we do, let me show you a consequence of, useful consequence of this form of Green's theorem. It's to evaluate the area R. So this area R, it could be this one or any arbitrary region, like the first one I drew. Okay, so the area of a region R and this is going to be enclosed by our curve C. So just again real quick, it could be this sketch I drew at the beginning. You have some curve C, and then this is the region enclosed by it R. Now the area of this would be defined as the line integral over our closed curve C of just x dy, which is also going to be the same as negative of this line integral over C of y dx. And then that's also the same as 1/2 of this line integral over C of x dy minus y dx. So this would be how to figure out the area. Alright, so now we're ready for the second form of Green's theorem. So again, this is the theorem, but this is flux form. The first one was circulation form. And flux form of the theorem, you're still taking this line integral over your curve C, but this time your vector field is being dotted with n, where n is an outward unit normal vector on C. So let me just write that here. N is the outward unit normal vector on C. Okay, and what this form of the theorem says is that this is the same as the line integral of C over C of little f dy minus g dx. Okay, and then this is equal to, and again, this is going to relate to a double integral over our region R, and this time it's the partial derivative of f with respect to x. If you recall, last time it was with the circulation form, it was partial derivative of f with respect to y. So now it's the partial derivative of f with respect to x plus the partial derivative of g with respect to y, and this is dA. Okay. So I don't think you could see the dA, but it's in the back there. So this is our flux form. Now, just like the integrand on the circulation form, this had a special name. It has a special name here as well. This is called the two-dimensional divergence of f. So 2D, I'll just say 2D divergence. Actually, let me scoot over. So two-dimensional divergence. Okay, and with the other form, remember, if the curl, that the integrand was the curl, if the curl was 0, it implied that your vector field was irrotational or conservative. If this divergence is 0, so note, if divergence, I'm just going to abbreviate, if divergence equals 0, then that means that f is what we call source free. So f is source free. Okay, so if you would just evaluate this quantity here, if it's 0, you would say that your vector field is source free. Okay, so let's evaluate an example with using the flux form of our Green's theorem. Alright, so we want to consider this integral, line integral here over our closed curve C. We'll just jump straight into the integral. This is going to be 8x plus ln 8y dy minus 2y squared plus sine, hyperbolic sine, h dx. Okay, and then our region C, we're assuming that the curve is oriented counterclockwise, and then C, so let's define it here. So C, we assume it's oriented counterclockwise, and it's defined by the vertices of a square. So where C is a square with vertices, then we have 4 of them, 2, 4, 4, 4, 4, 6, and 2, 6. So let's actually just draw this curve C real quick. So we have let's go from 2, so our x is range from 2 to 4. So let's call this 2, we'll call this 4, and our y's range from 4 to 6, so we'll go a little bit higher here, 4 to 6, and it's a square formed by these 4 vertices, and it's assumed to be oriented counterclockwise. Okay, so this is C, and it encloses this region R. Right. So if you notice, we're going to use flux form of Green's theorem. We have this, this is our f, so look at this theorem here, f dy minus g dx. So this right here is going to be f, little f, minus g dx. This right here is going to be little g. And so to use this form of the theorem, we need the partial derivative of f with respect to x. So partial derivative of f with respect to x, well, the partial derivative of f right here with respect to x, this is just a constant then. So all we're looking at is this, 8x, partial derivative of that, or derivative of this term with respect to x is just 8. And then we want the partial derivative of g with respect to y. So now g, partial derivative of g with respect to y, this term here is just a constant. So partial derivative, we basically just consider the first term. This is going to end up giving us a 4y. Okay, so by this flux form of Green's theorem, I won't rewrite the whole integral here. I'll just say that our line integral from before, so I'll just, you assume it's this whole entire quantity here, is going to be equal to the double integral over our region R, and it's going to be the product of these two partial derivatives, so 8 plus 4y dA. Alright, so now all that's left to do is to define the limits on our region R, limits of integration, and then just evaluate this integral. Okay, so we have, notice that x ranges from 2 to 4, y ranges from 4 to 6, so we're going to go ahead and put y on the inside, so we have y ranging from 4 to 6 and x from 2 to 4. And this is going to be of 8 plus 4y dy dx. Okay. 2 to 4. Now, integrating this with respect to y, we end up with 8y plus, this is going to be 4, and then this is going to become y squared over 2. So this 4 is going to turn into a 2 when you divide out the other 2, and y squared. Okay, evaluated from y is 4 to 6. Then we still have dx. Okay, so let's simplify this real quick. We end up with 8 times 6 plus 2 times 6 squared minus, let's go ahead and give this some parentheses, minus 8 times 4 plus 2 times 4 squared. Okay. If you simplify what's in here, so you'll end up with 48 plus 72 minus 32 minus 32. This whole thing becomes 56. So 2 to 4 dx. Okay, so now we just have to finish this off real quick. So let's move up here. So we have the integral from 2 to 4 of 56 dx. So we know that that's 56x evaluated from 2 to 4. Okay, so this is just going to be 56 times 4 minus 56 times 2, which ends up giving us 112. Alright, so that's using the flux form of Green's theorem.